right, this is the first lesson in Unit 8. There are two main topics that we're going to talk about in Unit 8. Unit 8 is split in half, and what we decided to do in the best interest of your grades especially is we're going to give you a mini test, which is the first half of the test after the first half of the unit, and then we're going to give you the second half of the test after the second half of the unit. All right, I also want to ease your mind because of the difficulty and how varied all of these are. The test will be 30 minutes. Just to give you a heads up before we even start the unit, each section is 30 minutes. You will be given 6 problems, which you choose 5 of the 6. So there's not a lot of room for error. You really do need to know how to understand and manipulate and do the things that we're going to do. And today is the intro lesson to that. This is actually not the first. What we're going to do today in its simple form is not going to be on the test. What we're going to do tomorrow will be the first type of test questions that you'll see. So this is just going to lay the groundwork, making sure that you understand what the notation means and the process, and then we're going to kind of blow it up and make it a lot harder. Righty? Again, as I said earlier, how you do in this unit is a big indicator of which level of calculus you should be in. The reason I say that is because if you think about what we've done in this course, we've done linear equations, quadratic equations, rational equations, radical equations. We have then went on to exponential. We went on to logarithmic. The big aha moment is now we're going to do trig equations. Okay? Trig equations and what we learn in trigonometry, that is the heart and soul of what you're going to do in calculus. It's also really, really vital to things like physics. You know, things like if you're in a car accident, how fast someone's going, all of those triangles and whatnot are going to come down to simple equations like this. Those of you who have taken physics, there's 2 types. There's algebra-based physics, which are all formulas, and then there's calculus-based physics. Those of you engineers and science majors, you're going to be in the calculus-based physics world. Okay? So that's where you're going with this. It's an application specifically of math. Like, why do we need to know this? Well, that's how you solve these types of problems. There is no other real shortcut for it. So what I want to start out with here is in the middle of the board, I have this expression written that says sine of x. And in not the last unit, but the one before that, we did graphing. Remember graphing? And you did an extra credit assignment where you made a table where x was the radian values. Does this ring a bell? And y was the actual sine values. Yes? These are called trig expressions. They're not equations. They're not functions as of yet when they're written in this form. And as you can see on the right-hand side, I made a list. We've got sine of x, sine of t, sine of theta, sine of alpha, sine of beta. I mean, there's a whole bunch of Greek letters that they may choose. You'll find that in all of the problems, the letter that is symbolized here for the angle should be consistent. So in the whole problem, you should have x's. In the whole problem, you could have t's. But these are units that stay together. So we're not going to separate them and say, okay, here's sine, and over here we have x, and we're isolating x. That's not going to happen. Okay? So we want to start to see these as units. Now, if we go back to the unit circle over here, I'm going to write this in green out front. Do you remember from the unit circle, sine was roughly the y value? Cosine was x, tangent was y over x. Cosecant was what? 1 over y, 1 over x, x over y. If you don't know that yet, you need to definitely nail that down. Aside from the OA and H SOHCAHTOA definitions, the green definitions I just wrote up were the ones from the unit circle specifically. So if you know you have a unit circle value, those are the 6 definitions that you want to use. The reason why I want to review them are because we are now going to take cosecant, secant, cotangent, and tangent, and we're going to redefine them in terms of other expressions. So here's what I mean by that. Sine of x is sine of x. That's going to stay the same. Okay? But cosecant of x now can be 1 over the sine of x. First new alternate expression. And it makes sense because if sine is y, cosecant's 1 over y, then the substitution holds that 1 over sine is the same thing as cosecant. Cosine of x stays as is. Secant of x is going to be 1 over cosine x. tangent of x. Okay, so the last two, they're a little bit special. If you notice the definitions in green, y over x is tangent. If you had to guess, based on the patterning that we just did in purple, what do you think I'm going to now call tangent x? If the alternate definition is y over x, yes.
Cosine x over sine x.
Close.
Over tangent?
Yeah.
Oh, sine x over cosine.
Correct. This one's going to be defined as sine of x over cosine of x. So there's one definition. And cotangent then is going to be x over y, which is cosine x over sine x. These are not going to be given to you in a list. You have to memorize them. To me, I think the definitions in green, if you know those, make these definitions very, very easy. So when we're talking about cosecant of x, we can replace that with 1 over sine. Secant of x is 1 over cosine. Cotangent and tangent have alternate definitions written in purple. We're going to leave sine of x and cosine of x the way that they are. Okay, they're the simplest trig functions. There's no need to do anything with them. Okay. So, a couple things to notice, just to reiterate. When we are dealing with these expressions, we're going to pick one variable, x, t, theta, whatever it is. Notice in all of the ones I gave you up here, my variable of choice was x. This x has nothing to do with the x of the unit circle. All of these that are located inside the purple boxes, those x's are talking about an angle, like a radian value, a pi over 3, a pi over 2. Could be 30 degrees. Okay? Typically, when we talk about x and t, they're going to be radians. Theta can be degrees. And then the other Greek symbols, it really depends on the application of it. Questions so far? Okay. Let's move on to number 1 then. Green, number 1. The directions are always going to be to simplify for today. Number 1, simplify is cotangent x times secant x. Again, the x is inseparable from the trig function. They are units, expressions that stay together. So when it says to simplify, it's kind of like PEMDAS. The rules for simplifying, though, you get to pick from what you need or what you think. What's tricky about these are that in the beginning, on the simple ones, it's pretty straightforward. There's only one way to do it. As we get into more complicated ones, some person may try this method, it'll work. Some people may try this method, it'll work. There's numerous ways, which means when it gets to the test, theoretically, there's an infinite number of solutions that I have to read through every one of your problems in your work to make sure that you're correct. It's an awesome test to grade. It's a lot of fun. But it does tell me a lot about your thought process, which doesn't always happen when we're just solving down to one answer. So, in Simplify, this is an open-ended question. The goal is to take these two terms and make it smaller. Okay? Now, when I say two terms, this is technically one term. It's like a times b, ab, but we still want to make it look smaller. So we're going to use our definitions to do that. What is another version of cotangent? What does it say on the board? Cotangent is? Right, so we're going to go cosine of x over sine x, replace that, times secant of x, which is 1 over cosine x. So I'm going to use the definitions, the alternate versions, to substitute. And then I'm going to use algebra. So since I'm multiplying, what can I cancel? Cosine x's are going to cancel, which leaves me with 1 over sine x. And the definition of 1 over sine x is what? That's a fraction. What's less complicated than a fraction? That's going to be your final answer, cosecant of x. So if this is is my left, your right. If this side of the room, this row, I asked to tell me the cotangent of pi over 3 times the secant of pi over 3. They would do all that work. But this side of the room, I would ask them just to tell me what is the cosecant of pi over 3. These two things are going to be the exact same value. So doing all the work to plug in and simplify, it's going to give you the same exact answer as if we just found the cosecant of x. That's what we're trying to do here. CSCX, cosecant x. Okay. Also, as we move through these, you're going to find that there are 3 types of people in this room. There are those people who see this, it is so easy for them, and they absolutely love it. Every math teacher in this building loves doing these problems. Yep, we can get together for meetings and do trig stuff all day long. Love it, absolutely love it. You're not going to find a math teacher who says they don't love it. Then there's the people in the middle who are like this close to getting it right, and they're always like one step away in the beginning, and then all of a sudden the light bulb comes on and they get it, and they like that challenge of trying to get it and trying to get it right. People who like Sudokus, you know, you like doing like crosswords and things like that. That's the middle group. Then there's one group over here on the other side, and I hope you don't fall into this category. It's very few people who just don't have the background or the interest to really master this. Those of you that are in that category, calculus will be miserable for you. Sorry to say. Okay, we're going to try to push you to the middle or all the way over to people who love it, because they are a lot of fun, even though they might not look like it. Don't they look like fun? Awesome. All right, let's go on to number 2. So, number 2. Here we go. Looks like that. That is the phi symbol. And yes, I had to come over and check over here is my Greek alphabet. Now, when it says simplify, there's not really any specific direction as to what to do. However, in your experience in the past, whenever you've had parentheses that look like this, what did you do? You can start on the inside, but what's the easiest way to get rid of the parentheses? Distribute, which is what you should do in this problem as well. So if I distribute, I'm going to write it all out. Some of you will start to be able to skip steps, but I'm going to take the sine of phi times the cosecant of phi minus sine squared phi, which leads me to some notation. And the new notation is right here. If I take sine times sine, I don't put the squared at the end because that would indicate that the angle is being squared. You have 2 choices. The easiest and most useful, what you'll see in most textbooks, is sine squared in front, which means I have 2 of them written. The other option is to do this, but then we added more parentheses and we made it more complicated. Okay? I would prefer this, and you'll see that's how I'll do all of my work.
Isn't there 2, sort of a line in it? Isn't there 2 of those? So we'll do the 2.
No. No, because if you think about it, like what's the sine of pi over 3? You know what that is off the top of your head? Pi over 3 is the tall triangle in quadrant 1. What's the sine?
1/2.
Root 3 over 2. So what I'm really doing is taking root 3 over 2 times root 3 over 2. I'm not taking pi over 3 and squaring it, making it pi squared over 9. Does that make sense? I'm taking the actual sine value, whatever that y is, like here, substituting that and then squaring that. Root 3 over 2 times root 3 over 2. So that's why we write it like this, or we write it like that. All right, so that's the first notation piece. Now we have what's in purple. Now it's going to look like the first example, a little bit more complicated. Sine of theta stays the same, not sine of theta, sine of phi times 1 over sine phi minus sine squared phi. What happens when I take sine times 1 over sine? What cancels? Sine. Leaves me with 1 minus sine squared phi. Sad to say, we are not done. Well, what's the definition of cosecant? So I replaced it right here. And then when you take sine times 1 over sine, don't the signs cancel? Right? Because this is all one big fraction, so the signs all cancel. But then when everything cancels, you're left with a 1. Okay? All right, now, this problem is not done. We're going to move over here to this right side where it says Pythagorean identities. Do you know what the Pythagorean theorem statement would be for the triangle on the board? Should be easy. Pythagorean theorem, Jordan? Okay. A squared plus B squared equals C squared, correct? Everybody with me? Okay. So now, I'm going to take that same triangle. I'm going to erase it. I'm going to put it in orange. Come over here. Here, here, this is y, this is x, this is 1. All right, so now, right triangle, x value, y value, 1 is the hypotenuse. What would that Pythagorean theorem statement be? Yep, x squared plus y squared equals 1 squared. Right, if we take a right triangle, place it in the coordinate plane, we assume it's a right triangle that's one of the unit circle values. Now, according to our definitions, what's x and y? What's x? Cosine. So this is going to be cosine squared x plus sine squared x is equal to 1. This first is known as a Pythagorean identity. Pythagorean identity. It's a definition. It makes sense with what we've already known. Pythagorean identities only work on the unit circle. Cosine squared plus sine squared equals 1. The reason why we're introducing Pythagorean identities are because if I rearrange this, can't I get cosine squared x is equal to 1 minus sine squared x? So because of that, 1 minus sine theta is cosine squared, not theta, but phi. That's my final answer. Which is way smaller than what I started with in green. Okay, no dumb questions. This is a lot of new information used in a different way. New information to you as in before Thanksgiving, none of this even existed in your world. New. So what questions do you have on what I did? What explanation? Go ahead.
How did you get from that problem to the cosine?
Well, I guess the easiest way to see it would be this. If I had something like square is equal to 1 minus heart squared, and over here I have 1 minus heart squared, does it make sense I can substitute that just for squared?
Yeah.
Okay, instead of hearts and squares, they're actual expressions. So notice I have 1 minus sine of x, sine squared x. Here I have 1 minus sine squared phi. And then I just substituted is cosine squared, so it is cosine squared.
You sub what? Oh, you just take that and put it.
Yeah, like I said that this is equal to this, so I took that out and replaced it with this,
Okay, and
which
then
is much
you
smaller.
Start with that. You can't use x as your answer. You have to put the.
Yeah. Right, and you're going to find that all of the definitions that I give you will be in terms of x, but that's why I said it could be a t, it could be a theta, it could be some other symbol, which you still use the definitions for. All right, ask away. Some of you look a little mystified. scaring you. This is just the intro lesson. So if this is confusing, please ask at any point, any step. We're all good. All right, so I'm going to do this. I'm going to erase number 2. I'm going to write number 3 in here in a second. I'm also going to get rid of all of this extra Pythagorean theorem stuff and just go right with Pythagorean identity number 1 is what I have here in orange. Okay. Now, one other little caveat here to using Pythagorean identities. Pythagorean identities have to be with squares. If you have a 1 minus sine x, you can't use a Pythagorean identity. You have to have something that relates and can be simplified back to cosine squared plus sine squared equals 1. Okay, so it's got to involve squares. So now let's take a look at number 3. Number 3. Secant of x plus tangent x. Secant of x minus tangent of x. Does this look to any of you similar to problems we did back in prerequisite? What do we call those problems? It's a certain form. Or can you give me something similar to it with just letters? No trig? You got to recognize it in order to use it. What about the FOIL? It's a special case of FOIL. Which one is it? Where the middles cancel, the difference of squares? Yes? Something like this where it would be like x minus 1, x plus 1, difference of squares? Right? When you multiply it out, what do you get? X squared minus 1. There's no middle term. The same thing is going to happen here, but we're going to write everything out so we can see it. Right? So my next step is to FOIL this. Secant times secant is secant squared x. Secant times negative tangent is negative secant x tangent x plus tangent x secant x minus tangent squared x. So I want you to write it, and then I want you to think about it for a second. Why do my middles cancel? They don't look alike. My middles are here and here. Does order matter when we multiply? No. So it's like saying negative AB plus BA. They both cancel because we can always change the order of them. So since this is multiplication, these two are going to cancel. It leaves me with secant squared x minus tangent squared x. All right, sad to say we are not done with this problem. Here's the reason why. There are 3 Pythagorean identities. The basic one is cosine squared plus sine squared equals 1. If I take each one of these terms and I divide them by cosine squared x, divide by cosine squared x, divide by cosine squared x, what is cosine over cosine? 1. Okay, so let me grab my orange. So I have a 1 here, plus, what is sine squared over cosine squared? Y over x, which is, I heard it, tangent, plus tangent squared x is equal to 1 over cosine squared. Secant, but since it's squared, it's going to be secant squared x, correct? This is your second Pythagorean identity. Okay. So if I look over here, what can I rearrange this orange box? I can rearrange it to say that secant squared x minus tangent squared x is equal to what? 1. So this is the same thing as 1. All right, time for questions. Pythagorean identity, know the basic one. Divide all three of them by cosine, you get the second one. Now, just for fun, what if instead of dividing everything by cosine squared, what if I switch this to sine squared? What's my new Pythagorean theorem, my third one? Cosine squared over sine squared is cotangent squared plus 1 is equal to 1 over sine cosecant squared x. That is the third and final Pythagorean identity. All right, I'm going to erase this black. Go ahead. You got it? Okay, so the work I have over here to the far right says secant squared x minus tangent squared x equals 1. That's what the substitution is here to get 1. Go ahead.
How do you know which one to put the equation of
Okay, so here's what I would do. I would have a note card probably for right now, and I would write all three of these on there. Okay. The day of the test, the first one's pretty easy to memorize, right? Then I would just quickly maybe just write that underneath for a visual for me and then generate these, or you can memorize them. I didn't memorize them. I always regenerate them. So when I was looking at this, I was like, oh, you know what? I need secant. Secant's 1 over cosine, so that's why I divided everything by cosine. Like, that's kind of my thought process because I didn't want to add more memorization that wasn't connected to something. So I would say have these three written down somewhere, spit them back out so they're ready for you for a test, and then just use them as you need them. All right, any questions in this one? Green to purple, purple to black, black to orange. When you look at it, when you go back and relook at it. Believe me, there are no stupid questions. This is not, as you can see, this is very high level. Nothing? We're good. Put it this way, does it make sense? Even if maybe you don't feel like you can do it on your own, does it make sense logically to you? A little bit? Do I need to get a cooler room tomorrow? You're like going to sleep.
Maybe we need to put a crack in the window.
Oh yeah, you can open the windows. It's fine.
It's too warm in here to put a crack in the window.
Yeah, it's up to you. All right, 1, 2, 3. All right, so we're on number 4 of 6. All right. All right, next problem. Secant squared x, tangent squared x plus secant squared x. What is it that pops out to you about those two terms? What's the same? That secant squared x, right? You see how it's like the same? That's going to help you if you analyze what you're given. So in this problem, to solve it, the first step is actually going to be to GCF. So now we're not doing what we did in the last one where we FOILed. We're not taking like the problem before and distributing. We're going to work in the other direction. And the reason is because I gave you something that didn't have parentheses. So to simplify it, that would make the most sense. So if I come over here, I'm going to take out secant. Let me find a different purple marker.
Yeah, because it's hard for me sometimes to read the letters.
I'm going to take out secant squared x, and I'm going to say tangent squared x plus 1. All right, so those of you who your brain goes 100 miles an hour, What do you see on the board that's going to simplify the purple? What is tangent squared x plus 1 known as? Second Pythagorean identity, what can I replace 1 plus tangent squared with? Secant squared. So take a look. This here is my Pythagorean identity that I'm going to replace with secant squared x. But I still have on the outside the original secant squared x. That didn't change. So what is secant squared times secant squared? Secant to the 4th. Yes, no, maybe. This is not a good unit not to do your homework in, unfortunately. The only way you get good and get better at them is to do more and more of them and kind of work at them, as you're going to start to see. All right, number 5. No questions, number 5. Oh, this is my favorite one. 1 minus 2 cosine squared x plus cosine to the 4th x. All right, first question. How many terms are in this problem? How many terms are people?
1, 2, 3.
There are 3. Number 1, negative 2 cosine squared x. That's number 2. And number 3 is positive cosine to the 4th x. What we want to start to do is match them up to similar forms. So if I kind of look at this, I'm going to draw this down below in case you don't see this. 1 minus 2c squared plus c to the 4th. See how I took out the trig and just went with letters? If I rearrange this, c to the 4th minus 2c squared plus 1, didn't you learn how to factor this? Right? So if I rewrite this as cosine to the 4th x minus 2 cosine squared x plus 1, I'm changing the order. It looks now like something that I can factor that I've seen before. What can I factor this into? Well, cosine squared x is going to be my intro, because cosine squared times cosine squared is cosine to the 4th. And now I need the numbers that multiply to give me 1, but add to negative 2. What multiplies to 1, but adds to negative 2? Negative 1 and negative 1. Right? If you look outer, negative 1, inner, negative 1, that adds to negative 2. And now, you're going to start, some of you are going to start, hearing little warning bells. Picked up the orange marker. Why? What is cosine squared x minus 1 known as? Cosine squared x minus 1 is equal to, close, negative sine squared x. Take this. Cosine squared is what I have to lead with, right? So I've got cosine squared x minus 1 is equal to, move this to the right, negative sine squared x. So over here, these are my Pythagorean identities. Negative sine squared x, negative sine squared x, which leaves me with sine to the 4th x. Yes, it becomes positive 1. Probably wouldn't matter, but this is where I have to read through all of your work, because the substitution should be with a negative. Questions on that? Too fast, or are we okay? Take a minute. Anything you want explained again? Why did I? How did I? You're going to need to be on the lookout for these triples that are factorable. Most of the ones you're going to have will be cosine squared, cosine, and a number. This is just a special case I wanted to cover first because it does come up. I'm pretty sure you know how to factor basic ones that are like c squared minus 2c plus 1. Any questions with Pythagorean theorem? Pythagorean identity, rather? All right, last one. Number 6. There you go. Your friend fractions are back. Yay. We covered imaginaries with conjugates. You're going to need conjugates a lot in this section as well. So overall, the LCD is going to be 1 minus cosine x times 1 plus cosine x. Yes, LCD-wise? All right, so let's do that. Let's take 2 over 1 minus cosine x plus 2 over 1 plus cosine x. And let's multiply by the LCD. So my LCD is going to be, switch colors, the quantity 1 minus cosine x. This is not pretty, 1 plus cosine x. What am I missing from the first fraction to get the LCD? What does the first fraction need to get the LCD? 1 plus cosine x. Okay, so this is going to get multiplied by 1 plus cosine x. What's the second one missing? 1 minus cosine x. Okay, so my whole denominator is the LCD. 1 minus cosine x, 1 plus cosine x. Up top, I'm going to get 2 plus 2 cosine x plus 2 minus 2 cosine x. Too fast? Are we okay? What cancels?
The 2.
Which 2's?
2 cosine x.
Yep, and negative 2 cosine x. They're opposites, they cancel. So what am I left with up top? 4. So I'm going to go up here. I've got 4 over, what is the product of 1 minus cosine times 1 plus cosine? That's difference of squares. We did an example earlier. What do you get when you multiply those together? 1 minus cosine squared x. Okay, what is 1 minus cosine squared x known as? One minus cosine squared x is sine squared x. So if I look here, 1 minus cosine squared x is equal to sine squared x. So this gets replaced with sine squared x. I'm almost done. What is sine in the denominator? Which definition over there has sine in the denominator? Cosecant. And how many sines are there here? 2. So my final answer is going to be, I'm going to write it in black here, 4 cosecant squared x.